Welcome friend to my another episode of Dr. Research Explain. Today I'm going to discuss about the absorption spectroscopy, and I'm choosing this topic today because this is a very important thing to understand in case of a student who are in new doing their um, MTech or first year of research in nanoscience and nanotechnology, because they need to measure the absorption of some synthesized material, like they are actually if they are in nanoscience and material science, they need to synthesize some nanomaterial, and the first signature whether your sample is prepared or not is very uh, what I can say, very elegantly measured by the absorption spectroscopy. That means if you get some signal that is some characteristic features, like in case of a general nanoparticle, you will get the band depth linkage absorption. In case of a meta nanoparticle, we will get the surface plasmon resonance absorption spectroscopy. So using that absorption spectroscopy, you readily understand that your material is synthesized, and you can explore further. So this is a very unique way to understand whether your material is synthesized or not. So I will just discuss the basic things, and what you need to understand to elegantly measure or very simply measure the absorption of your synthesized sample. So I like to discuss some theory before going into the deep. Actually, you need to understand the Beer-Lambert's law, which is very important here. So Beer-Lambert law, actually Beer-Lambert's law tells that absorption, which is the measurable quantity, which we'll going to measure using the uh, UV visible absorption spectrometer, is simply A equal to epsilon and C into L. What is epsilon? This is the extinction, molar extinction coefficient, and C, which is C is the concentration, and L is the path length of the cuvette path length. So extinction has the unit of liter per mole per centimeter inverse, and the concentration is simply mole per liter inverse, and length is centimeter. So if you measure, if you just multiply those things, it's become dimensionless, which is the absorption here. So suppose say you have a cuvette here. Cuvette are generally a polished quartz, and it has a zero absorption in your measurement range. That means if your absorption spectrometer scan the sample over the distance of 400 to 800 nanometer, then over this range, this cuvette has a zero absorption. Otherwise, it will actually interact with your sample absorption, so you will not getting the right measure. So suppose say this is a cuvette of path length, suppose say x, and suppose radiation of I, zero, incident on the first surface. And after passing through this sample, if I is the intensity of the emanated radiation, then we can write down some equation like the attenuation equation, that is di by dx as a negative quantity, because it is reducing with over the distance, is simply proportional to I. So if you just use the equal sign, then you can take a constant here. So is this the attenuation constant mu? So just rearranging this, you can writing like this: di by I is simply minus of mu of x, and by integrating both sides, we will get something like ln of I is equal to minus of mu of x. This is actually dx, not x, and ln of c. So if you just rearrange this equation become ln I by c is equal to minus of mu of x. That means I equal to simply c to the power minus of mu of x. Now, if you use the boundary condition like x at x equal to 0, I is I0, then you can get a simple equation That is is I 0 e to the power of mu of x. Well, this is the attenuation equation. So uh, this is the basic of the Beer's-Lambert law. Now, the absorption, which we generally measure using our spectrometer, is simply like absorption is minus of uh, ln I by I zero. Okay, and the transmission is simply ln of 1 by a, and it is actually the percentage transmission. So if you measure your absorption using your absorption spectrometer, you will get the data within certain range of absorption. That means your absorption spectrometer has certain limit. I mean, that means over that limit it gets saturated. So you will get up to 0 to a certain limit. Say suppose say P. P is the highest limit of absorption in your spectrometer. So the important thing is here, you need to prepare the solution according to the uh, saturation limit of your absorption spectrometer. Suppose say, actually we are measuring very low concentration of the sample. Suppose say you want to measure the 1 molar solution of NaOH. Okay. So you know the molar weight of the NaOH, which is 40 gram. So you need to dissolve the 40 gram of NaOH in 1 liter of deionized water or distilled water. So this is not practical. So you just you can make 10 ml of solution. For that you need to have, I think, 0.4 gram of NaOH. Means 1 liter means 1000 cc. So 1000 cc contain 40 grams. So 10 ml will contain 0.4 gram of NaOH. So in that way you can also prepare the 1 molar solution of NaOH, and then you can measure the absorption using your absorption spectrometer. So this is okay if it is comes in the limit of 0 to P, that means your saturation limit. So if it is not so, then you can dilute the solution. Dilution, for dilution you can add some water, but in a very precise way. That means you need to prepare the solution of known concentration. So you can see the how the homeopath prepare their solution. That means the concentration means suppose you reduce the concentration by 10-fold, then you just take 1 ml of that solution, prepared solution, and then add 9 ml of water or DI water. Okay, so in that way you can decrease the concentration by 10-fold, and then you can measure the absorption. So this is the way of preparing the solution. Okay. Now, next big thing is that you need to have some baseline correction for that sample. Why it is so? Because say some sample like gerano. Okay, we prepare the gerano nanoparticle, and this gerano nanoparticle is not actually dissolved in water very elegantly. So you just dissolve in ethanol of say ethanol, and you put in sonication before every measurement. You need to sonicate the sample to prepare a homogeneous mixture. Otherwise, you will not get the very good data. So you need to actually nullify the contribution of ethanol in the absorption of geranium. So in the most of the cases, we have used actually the double beam spectrometer, and this double beam spectrometer contains the two QVT uh, uh, set actually, one for the sample and another for the baseline correction. So you just put ethanol in both this QVT and run the spectrometer, scan the spectrometer, and for that you will get the absorption is very near to zero, because in that way you can nullify the contribution of ethanol. And after the baseline correction, then you can replace the sample QVT with the actual sample, that is the Gerano solution, and then measure the absorption. You will get some data like this. If it is Gerano, then you know that there is some band edge absorption. So this is the lambda and this is the absorption. And in that way, you can calculate the absorption. And from this absorption, you will actually get some visualization that whether your sample is prepared or not, that is the some nanoparticle is prepared or not, and you can actually find out the energy band gap from some method, which is not relevant here. I will discuss it later on. Now, to measure the absorption coefficient. Now, the absorption cross section is a sigma, which is like this sigma, and this is in centimeter square, is simply alpha by n. Now, what is alpha? Alpha is 2.303 into A divided by n. N is here is a very tricky thing, and n is not the actual concentration, it's the actual number concentration, it's the number of newtons in the solution. So it is related to the actual concentration by the formula C, and which is equal to simply N into 1000 divided by Na. So if you replace this in above equation, then we can get a 2.303, and this is actually uh, A into C, and it's not C, C is here, C into N. Okay. So if you just write down like this, 2.303, and this 1000 is also here. So 2.303 into 1000 divided by Na, and this is equal to A by C. And what is A by C? Yeah, we know from Beers-Lambert law, epsilon CL is A. So epsilon L is equal to A by C. So you replace A by C with epsilon L, and the most of the case L is 1 centimeter. So this becomes 2303, and this is Na, and this is simply epsilon. So this is a beautiful formula. With the help of this, you can actually measure the actual absorption cross section of the sample. That is different type of sample like GNO or silver nanoparticles or any other nanoparticles. You can actually measure the absorption cross section. It comes in centimeter square. So using the absorption measurement, you can measure the absorption cross section, and I'm ending my discussion today here. If you like this video, please subscribe the channel, and let me know what you else want to hear from me. Uh, so please do comment in the comment box, and please press the bell icon. So thank you for your patience. Thank you.